Hello and welcome to the next webinar of Würth Elektronik. My name is Vivian Neuberger and I will moderate this webinar today. Today's topic is calculation, simulation and measurement of 800V EMC filters. I would also like to welcome Andreas Nadler. He's Field Application Engineer at Würth Elektronik and he will do today's presentation. And afterwards he will answer your questions. And now I would like to hand over to you and wish you an exciting webinar today.
Thank you, Vivian. Hello and welcome to my presentation. Before we start with the 800V DC application grid filters, I would like to inform you if you have let's say normal one-phase filter application for AC grids, you can download the ANP015 for more information, but we will also send this via email to you as a link in let's say afterwards. And if you have a three-phase application, you can download the ANP137, which is then also gives you more information about three-phase, more on high-power applications. Well, today we're gonna start with the source of interference, just for basics. Then what kind of components for filtering do we need? How to design the filter, calculate and simulate the filter, and how to measure the filter, and what are the, let's say, the bottlenecks in the layout and in the design you have to be aware of. Let's say our source of interference is not the 800V system because of safety. It's a flyback converter, an isolated flyback converter. It produces a lot of common mode and differential mode interference, and this is important for us. The only difference is the, let's say, the high voltage, and from a component point of view, from an insertion loss point of view, there's not a big difference. In calculation, simulation is also not a difference. It's just the voltage rating of the component, which can be lower in such an application. But as you will see, I used 800V ready components for our filter here, so the simulation and the measurement is valid and also for higher voltage. Okay, for basics, we have two kinds of interference currents, the differential mode and the common mode. Differential mode is only happening between the plus and minus, and it's always the same path of interference like in, let's say, it's drawn in your schematic. That means it's very easy to follow this path. It's closing between plus and minus, in this case 800V and ground, or plus 400V and minus 400V. And usually you can filter this with let's say traditional LC, pi or T topologies between plus and minus. The root cause of the problem is the high di to dt, which causes some ringing with the parasitic inductance in the system, the ESL of the components, the ESL of the layout, for example. And it's usually we're talking about larger currents in the milliamps or in the amps range. Looking at common mode, it's much more tricky because it's always traveling an unexpected path, which is not written down in your schematic. That means it's coupled out via parasitic capacitors, and the root cause is usually a high dV to dt. That means you can overcome this problem. Either you slow down the voltage slope, or you try to, let's say, shrink the parasitic capacitance in the systems to protective earth. Usually we are talking about microamps in the range of common mode currents. You can filter this with shielding, with common mode chokes, and with Y capacitors respective to protective earth. Okay, and how can we measure this? Usually in the EMC test setup, we are using a so-called line impedance stabilization network. Inside the so-called listen is the 250 ohm resistors, where we measure the noise interference and couple them out to our, let's say, RF receiver. And from a noise current path point of view, the differential mode is traveling this way, the red arrows. That means the current is traveling through both the 50 ohm resistors in series. So from a differential point of view, we have 100 ohm impedance inside the listen. From a common mode point of view, where there are the blue arrows, we have the common mode currents are shunting back over the protective earth from both opposite directions. This means from an RF point of view, the 250 ohm resistors are sitting in parallel. Therefore, we have a resulting impedance for the common mode inside the listen of 25 ohms. Now, if you would like to measure them or calculate them separately to get, let's say, a proper filter design, so the filter will be not too big and too small, we have to measure them separately. Therefore, we see later on in the test setup, we separate the common mode and differential mode with the channels in the oscilloscope, channel 1 and channel 2. Therefore, for getting the differential mode part, we subtract channel 1 minus channel 2 divided by 2. And for the common mode, we add channel 1 plus channel 2 divided by 2. Why divided by 2? Because in the normal test setup, you measure only at channel 1 or channel 2, where you measure the combined interference. And if you do not subtract them by 2, divide them by 2, you get a level which is 6 dB too high. Therefore, to get the exact level like in a normal measurement, we divide them by 2. Okay, what are the minimum required components for, let's say, effective common mode and differential mode filter? So usually, we're starting at our grid side at the listen, then we need an overvoltage protection like a varistor. Then we got the X capacitor, external differential mode filter components. These are not mandatory, but I will show you why maybe they can be helpful. Then we need a common mode choke, which consists of the main inductance, which helps us in common mode, and the leakage inductance, which is effective working then for differential mode. A second X capacitor, this is also not mandatory. I will also show you what can be the benefit there. And we need the Y capacitors from the plus and minus to protective earth. They are helping then to shunt back the interference noise to the device under test. Very important is the overall filter structure for common mode and differential mode to place the components on the correct side, let's say, especially the capacitors. So from common mode point of view, we have a high impedance noise source because we have capacitors in the picofarad range which couple the noise out. So the XC is usually in a kilo ohm range. So high impedance, therefore we placing directly in parallel to the device under test on this side our Y capacitors. These are forming a, let's say, a capacitive divider with a lower impedance to shunt back the noise to the source. So our goal is to shunt back everything to the origin. So we do not measure any interference in the listen. And the main inductance of the common mode choke is then placed before the listen impedance. So high impedance of the inductor, low impedance of the listen. Low impedance of the Y capacitor, high impedance of the device under test, always the opposite. And for differential mode, we make it vice versa. Our noise source here is usually a low impedance noise source, which can be described, for example, by an input capacitor or a bulk capacitor in the system. So usually between 0.1 ohm or 1 ohm or 10 ohm is a good starting point as a noise source impedance here in the simulation, for example. Then we place at first the leakage inductance, because this is a high impedance, directly to the low impedance. And then parallel to the high impedance listen, we place a low impedance X capacitor. So that's the minimum, to place one X capacitor in parallel to the listen. The second X capacitor in our application here would be placed on this side. I will show you later on what's the benefit there. All right, so far as I know, there is no dedicated, let's say, normative, which are especially handling the requirements for 800 volt DC grids in, for example, data center applications. But there are a few normatives. I show the four in the second row here, which are interesting for our application. So what's interesting is what kind of overvoltage category, or how high is the surge level, creep edge clearance, UL, and so on. So all the safety requirements are written down here. And this is then a starting point for you, let's say, which kind of components do you need, how much creep edge clearance on your PCB you will need, and what's the overvoltage category. So usually we're talking about OVC 2 or 3. That means we have to test with surge levels from 4 to 6 kV, which is quite higher than a standard AC application, which is usually have an OVC or voltage, so surge voltage of 2 kV. The clearance is usually between 5.5 and 8 millimeters, depending on what kind of insulation do we need, basic or reinforced is usually required. The creep edge is depending on the pollution degree and the CTI of the material. And there we are talking about between, let's say, pollution degree 1, we have 2.4 millimeter at minimum with a high CTI. And in the worst case, we have 16 millimeter with a pollution degree free and a low CTI material group. And this is valid for basic insulation. If you have reinforced insulation, you have to double the values in the table. Okay, let's make a summary for the components. What are the requirements for them? So usually between plus and minus you need an X1 capacitor because this can handle up to 5 kV of surge. If you would like to use X2, they should have grade 2 or 3. That means they should have a high, let's say high test level. So 85 tests, so 85 degrees at 85% of humidity at 1000 hours. And the capacitors should, let's say, provide inside the tolerance level, or should stay inside the tolerance level after this test. Then it's a high quality capacitor. In this case, you need 2 in a row to fulfill, let's say, at least the 4 kV surge let's say, requirements here, because one X2 capacitor has usually 2.5 kV surge capabilities. From the Y capacitor point of view, epsilon 1 can handle 8 kV of surge and a working voltage of 1.5 kV, which is a little bit too much, to be honest, and it's a bulky and expensive component. In this case, a better solution will be a Y2 capacitor, which can handle 5 kV of surge and have a working voltage up to a certain temperature of 1000 volts DC, which is then sufficient for 800 volt applications. And usually the combo choke should also have at minimum 1 kV of rated voltage and should provide the required creepage and clearance on the component. From the varistor point of view, a 20 mm type is also mandatory here because of the, let's say, energy absorption capabilities. And usually this varistor will clamp the surge voltage at a level at around 2.5 kV. So 2.5 kV is then seen by the rest of the filter and the rest of the device under test. That means usually if you have a let's say a pretty big bulk capacitance in the system, this surge energy will be absorbed there and will not be a problem usually. Taking a close look at the required components, so from our side, we can provide you, for example, at the moment a CMB HV, which can handle up to 1.25 kV of rated DC voltage and up to, let's say, 22 amps of rated current. It's manganese zinc material. That means the common mode impedance, the curve we see on the left side. We see this is an effective component starting from 10 kHz up to roughly 10 MHz. We have a good insertion loss over the whole series of the whole components. And this is differential mode impedance. That means from 100 kHz also to 10-20 MHz, we have a good differential mode impedance curve and a good filter effect there. If you need insertion loss, the higher frequency, for example, in the radiated pattern from 30 MHz to 300 MHz, then you can extend this filter, which I have also done here with the so-called rod-core WESD. This provides you from 30 MHz to 300 MHz a good, let's say, impedance and therefore a good insertion loss for COM mode and differential mode, better than the pure manganese zinc COM mode choke. So you can combine the two components in a row. This is the varistor I have chosen here. It's the high surge varistor with a parasitic capacitance of 360 picofarad. This is then also interesting maybe to put in the LT SPI simulation you will see later on. The capacitors for the demo I used for the Y2 capacitors, our FT epsilon 2. They can handle 1000 volts at up to 85 degrees. Can handle surge up to 4 kV easily and are in the range from 1 nanofarad to 470 nanofarad and from a pitch from 10 mm to 27 mm roughly. So the creepage and clearance is enough with this kind of component. It has a Y2 and a X1 rating. For the X2 capacitors, if you would like to use them, I would recommend you the FTXH. It's a THB type with a high, let's say 85 endurance test. So it's a very stable and reliable capacitor. The drawback is it can handle only 630 volts and can only handle surge up to 2.5 kV. So in 800 volt application, you have to place 2 of them in a row between the phases. Therefore, I used for the test, as we have no X1 capacitor so far, we will expand our portfolio with it, but we are not ready yet. I used a standard DC link here as an X capacitor. The drawback here is it has only a surge level up to 1.8 kV, so no 5 kV than a normal X1 rating, but the working voltage can go up to 1500 volt DC, which is then sufficient for this demo. I just would like to have the capacitance, the voltage rating, and let's say the creepage and clearance here. If you need, let's say, a plug or a terminal block which can handle the creepage clearance, the voltage and the current, then our TBL series 2546 is a good choice for it, as we have a clearance over 8 mm and it can handle, let's say, over 1000 volt of DC voltage and up to 24 amps in the VDE rating. Very important from, let's say, EMC point of view is how you connect the Y capacitor terminal on the one side to the protective earth, and therefore I use the steel spacers, which provides me a very low parasitic inductance to connect the Y capacitor terminal at the lowest possible impedance to the rest of the housing or the shielding you will see later on. All right, let's take a look at the test setup, which you can do on your test bench by your own, for example. What we need is an oscilloscope with FFT. Ideally, it would give you a dB microvolt in the vertical range, and horizontal you can switch to logarithmic, and the resolution bandwidth should be set to 9 kHz. Then you have the same optics like with the normal test receiver. Then you need an isolation transformator to isolate the COM mode interference from the factory you're sitting in or the office you're sitting in into your test system in the lower frequency range. Then you need a supply, of course, which should have at least the best would be very clean DC supply. The listen you can do by your own or you can buy one, whatever. The filter PCB itself, then the noise source, and in this case an ohmic load. And all of them are sitting on a metal plate, on a conducting metal plate. This is simulating the EMC chamber, because usually the EMC chamber is also a closed Faraday's cage, and only in this environment the COM mode currents are following a defined path back to the listen. And with this test setup here, you can simulate the same environment nearly like in a normal test setup. So that the COM mode from the noise source and the filter is shunting back vice versa to each other where it's supposed to be, and to the listen like in a normal test setup. And to make sure we have a very low impedance in this test setup, I also used not only the steel spacers here on the filter PCB and the steel spacer on the listen for the PE connection. I also combined them here with a conductive mesh. As I have no screwed connection here, the conductive mesh helps me to get always a very low impedance connection to the metal plate, even if it's a little bit uneven and there is some, let's say, scrappy surface, for example. All right, let's make a first measurement. And the first measurement looks like this. If you make the conducted combined measurement, that means we measure COM mode plus differential mode combined, as we do in the normal test setup, in the normal EMC chamber test setup. We can see if we place no filter there, our device on test producing at the switching frequency at 300 kHz a lot of noise. So this is the fundamental frequency, the frequency in the lowest frequency range of the highest amplitude, and our filter, let's say, simulation calculation must be, let's say, directed to this frequency, because I always look at the lowest possible frequency, because this defines the lowest filter corner frequency, and the lower the filter corner frequency, the bigger the components will be. That means I have to look at this frequency here and take a look how big is the amplitude. And if I know my limits, in our example here, I'm using the class B limits, which are the most strict one. I have to get at least 60 dB of damping to get enough headroom between the limits and the noise. But with this measurement, I cannot separate common mode and differential mode, and therefore it's not that easy to design a filter properly. Because if I say, okay, let's assume the common mode and differential mode is at the same height, then, which is usually not the case because one of them is dominating, then the filter components or the filter overall will be too big and too expensive and too bulky. So it's always a good idea to separate the common mode differential mode with a separate measurement to get the really required damping in common mode and in differential mode separately. And how do we do this? We take a listen with two RF outputs simultaneously. Then we feed the signals from the RF outputs in channel 1 and the second one in channel 2. Then we make two math channels. Math channel 1, I make a subtraction, channel 1 minus channel 2 divided by 2. This gives me the differential mode, the red one. I feed this information then in the spectrum. And the second math channel, I make a calculation of channel 1 plus channel 2 divided by 2. And I feed this information as a basic for spectrum 2. This is then the common mode. And now I can see the common mode has much higher levels than the differential mode. And therefore I can see, okay, the common mode filter must provide me 60 dB of damping, and the differential mode part of the filter must provide me only 40 dB of damping. And with the first measurements without separation, both of them have to be, let's say, 60 dB as an assumption, and therefore the differential mode part would be bigger than required in the end. So maybe it's not a good idea. So it's always a good idea, in this case, to separate them to get the really required damping for our filter in the next steps. Okay, let's do the math. It's not that complicated. So this is the structure of the filter. I have a pi structure for the differential mode. That means one X capacitor, a second X capacitor on the another side of the inductors. I use the stray inductance of the common mode choke and the external rod core inductors. These are giving me the leakage as the overall differential mode inductance if I add them together. And let's say the X1 and X2 capacitors are then combined in a series from an RF point of view, which gives me then the capacitive part. And this structure, as we have three, let's say, stages inside this filter, a CLC stage, we have 60 dB per decade from the corner frequency of damping. So a very steep curve, which gives me a lot of insertion loss very fast. From a common mode point of view, I have the main inductance of the common mode choke and the two, let's say, in my case, are 4. But overall, from the Y capacitors, from the plus and minus to protective earth. And this is only an LC stage. We have 40 dB per decade from the corner frequency. So not so steep insertion loss like the CLC. Before we start with the rest of the calculation, we need to define the corner frequency for common mode and for differential mode. For all of them, this formula is valid in the end, and the corner frequency depends on the switch on the, let's say, the frequency of interest to filter. In our case, 300 kilohertz, which is then also the switching frequency of the converter. Then I need to put in here in the exponent the required damping. So that means for common mode I put in 60 dB, and for the differential mode I put in 40 dB. And then, depending on what kind of filter structure I have, for the CLC I have 60 dB, and for the LC I have 40 dB in the counter. And therefore I get two corner frequencies. For common mode it will be 9.5 kilohertz, and for differential mode it will be 65 kilohertz with this calculation. And for the CLC I need to make one step more than with the LC, because from the CLC, the pi filter structure for the differential mode, I have two X capacitors, X1 and X2, and they are sitting from an RF point of view in series, and therefore the effective capacitance for the later following calculations is the series connection of X1 and X2. The drawback here is, in the end, if I have two 1 microfarad capacitors, the resulting effective capacitor is only 500 nanofarads, which is then the drawback of this CLC. But the positive thing is I have 60 dB per decade. All right, so we calculate the corner frequencies. We know how much damping do we need, 40 dB and 60 dB. Now we can make a start of the calculation, and usually a good starting point is the Y capacitors. As we have a DC system, the leakage currents are not a big issue here. In AC applications, the leakage currents in the systems are critical because from a safety point of view. But we have here a DC systems, therefore we can let's say choose very big Y capacitors. So I started with 247 nanofarad from plus 2 PE and 247 nanofarad from minus 2 PE. Gives me in total 4 of these capacitors, so the total effective capacitance CY is roughly 119 nanofarads. In the next step, I can calculate now the required COM-mode inductance to get the corner frequency. So therefore, I put in here in the Thomson equations the corner frequency from above, then the total Y capacitance, and then I can calculate how much inductance from the COM-mode point of view I will need. It's roughly 1.5 millihenry. Usually it's always a good practice to choose much more than the calculated one due to the tolerance of the COM-mode chokes, for example. They have plus minus 30% usually. So I chose here a 1.61, which is pretty close to this. In reality, maybe a 2.2 will be a better choice here to have more headroom. Then the next step is to calculate the leakage inductance of the COM-mode choke. If it's not written down in the datasheet, you can use, for example, the impedance curve in the datasheet or in the expert. You take the differential mode impedance curve, look at the frequency, for example, where the impedance curve is very linear in climbing. For example, in this case, 100 kilohertz. Then I can read on the left side the impedance at this frequency is 9.6 ohm. And then I can calculate the resulting leakage inductance, which is roughly 15 microhenry. Additionally to this 15 microhenry, I have the 2 rod cores, which are sitting in plus and minus in series. I have to add them to get the complete differential mode inductance. In our case, it's then 35 microhenry. And the last step is then now I can calculate the required X capacitance, which is then the corner frequency of the CLC filter with the 35 microhenry. This gives me a total effective capacitance of roughly, let's say 170 nanofarad. As we have a series connections, we need double the value from the single capacitor. So let's say 330 nanofarad at least per capacitor. But as these capacitors see a lot of, let's say, surge pulses in reality, so the X capacitor is the component in the system which degrades the most, to be honest, because depending on where your device under test is installed in the world, you have better or poor quality grids. And the more poor quality grids you have, the more surge pulses you will see, the more it will degrade the X capacitor and therefore the capacitance and therefore the EMI filter. So it's always a good idea to choose a much more bigger value also to have more headroom for the future. All right, let's take a look at the schematic and PCB. I, let's say, designed this filter with Altium. So here's the Altium schematic with the varistor, the bleeding resistors, the first X capacitor, the external rod cores, the main COM-mode choke, the 2 Y capacitors to protective earth, another 2 Y capacitors to protective earth, and the last X capacitor before we go to on the unit under test. From a layout point of view, we're starting on left side with the grid, the varistor, X capacitor, COM-mode choke, rod cores, and Y capacitors. What's critical here is, of course, the creepage and clearance between plus and minus have to be, let's say, in a certain level, which is then required from your application. Then it's always a good idea to place the capacitor and the inductor next to it in a 90-degree angle to, let's say, avoid any E field and B field coupling. And the most critical part is usually from an EMC point of view, how you connect the Y capacitor terminal to the protective earth. So this connection here must be very short, as wide as possible, so that the impedance, the ESL, should be as low as possible. And therefore, these spaces is a very good idea to connect here with the Y capacitor terminal to the reference shielding. Do not connect them on the PCB. So make no connection on the PCB itself, because then you get maybe a COM mode to differential mode conversion on the PCB, and you degrade your filter. Your protective, let's say, protective earth reference is usually your shielding. In my case here, the conductive metal plate. All right, let's do the simulations before we make the final measurements. For simulations, I used a free tool called LT-Spice. I think most of you know them already. So for differential mode, we have to take the 100 ohm in the listen, because the 50 ohm resistors are sitting in series. Then we have the varistor capacitance, which is also effective between the phases. The X capacitor, the rod cores, the COM mode choke, the second X capacitor, and the Y capacitors are sitting in series from an RF point of view between the phases. And we have a low impedance voltage source here. You can also put additionally a resistor with 1 ohm or 0.5, 0.1 ohm, or whatever your application is in reality. But LT-Spice usually provides here an ideal voltage source with a very low impedance, which is then a good starting point for differential mode filtering and differential mode simulation. All these components you will find in the standard LT-Spice library from us. The special components like the COM mode choke you find in the so-called contrib folder, which is also usually standard in the standard installation. And if you need any help there, how to use this part and how to simulate with this part, just contact us and we will help you there in this kind of application. All right, let's take a look at the insertion loss curve. We can see from a mathematical point of view and a measurement point of view, we said we need 40 dB at 300 kilohertz. And we nearly exactly get 40 to 42 dB in the simulation, which is perfect. And we can see the filter curve is rising and very stable up to, let's say, 10 megahertz before it's declined. So it's a good starting point for a filter here. It's not starting to decline after 300 kilohertz. So, but in the opposite, it starts rising the insertion loss and keeps it over a wide frequency range. COM mode is a little bit different. COM mode, we have not 100 ohm, but 25 ohm inside the listen, because the 250 ohm resistors are sitting in parallel. We connect the terminals in this kind to get the COM mode inductance of the COM mode choke, and we are placing the Y capacitors directly to ground. Ground is protective earth in this case. And we have as a device under test a current source, not a voltage source like before, because the current source provides us a high impedance. You can also add in series, for example, a 1 kilo ohm resistor, which is also a good starting point for the impedance of the common mode of our device under test. And this is what we get insertion loss in the COM mode. We required 60 dB, or we calculated 60 dB, and we got in the simulation 62, perfect. And also here the filter is very stable up to 10 megahertz, and after 10 megahertz it starts to decline in the insertion loss. So very good starting point to make our first measurements with the simulated filter. All right, if we make the separate measurement again with the filter, we can see we get in the COM mode perfectly over 60 dB as we wanted at the switching frequency, and in the differential mode we get the required 40 dB perfectly, very nice. But what we also can see that the filter is starting to degrade after 10 megahertz, so at 15, 20, 25 megahertz, we see the filter is starting, or is not good enough maybe from a COM mode insertion loss point of view. Let's see, because this is not the real measurement. The real measurement is both of them combined, which is done here. So here I have the combined measurement, so COM mode plus differential mode. We can see from 300 kilohertz to 10 megahertz is perfect. And at 15, 20, 25 megahertz, we are too close to the limit. And this is due to the, let's say, not perfectly chosen Y capacitors. They are perfectly chosen from a low frequency point of view, but as they are a THT wired capacitors, they have a very high ESL. So what can we do there? We can make an intelligent combination. That means we combine the existing Y capacitors and put in parallel a low ESL SMT type. But as the creepage and clearance is maybe not sufficient, I put two in a row of them together. So there are only 4.7 nanofarad, 2 in a row from each phase to protective earth. They cost not much, they need not much space, but the ESL is much more lower than compared to the THT part, and therefore we get over 10 dB better insertion loss in the higher frequency range, which is then, let's say, a very good starting point to go to the real EMC measurement. That's all from my side. Thank you for attending the seminar, and I'm looking forward to your questions.
How does the lower temperature affect the impedance curve?
Yes, the capacitors are affected with the low temperature and the inductor as well. So we test the components usually to minus 40 degrees, in some cases even to minus 55. Minus 40 means for the inductor, we are losing roughly 20 to 40% in worst case of the inductance value, therefore also for the impedance and insertion loss overall. It's very critical to understand that the combo chokes have from the factory plus minus 30% of tolerance. So always gives you in your calculation much more headroom in to the limits from the calculation point of view. So what I did was, let's say, good enough, but in reality, take into account the temperature, because also the capacitor is also losing roughly 5% of capacitance, and there's also the corner frequency is affected.
Okay, thank you for this answer. Now let's go ahead to the next one. Is there a way you from Würth Elektronik can support me a little bit with the design?
Sure. Usually, depending on where you are from, every country has an more than one FAE like me. So you contact your responsible salesperson with your, let's say, request, and then we will help you for sure.
Okay. Thank you. Next question. Do we need bleeder resistor for Y capacitor as well?
No, usually not. The bleeder resistor, it's in many, let's say, fixed installation. It's also maybe not needed. Usually you need a bleeding resistor for applications where you have a plug where you can touch it. So for example, in the normal AC applications, if you pull out the wall plug and then the regulation says in 1 second, the voltage at the terminal of this plugs must be under 60 volts.
Okay. Then the next question is there no need to add a damping network for the filter?
Sometimes this is necessary, depending on the structure, the impedance, and the quality factor of the components. So it's not mandatory in most cases, but there can be some applications during, for example, a surge test, where the LC corner frequency forms, let's say, a top. And when on this top, the surge pulse is applied, then the voltage is even higher than of the normal surge voltage. So sometimes it's necessary, but not often.
Okay, thank you. Then the next question, assuming an 800-volt automotive system, what about first X capacitors when subject to SIFE test?
So as far as I know, the SIFE test is then a voltage applied on top on the 800 volts. So therefore, a normal X1 or X2 capacitor is not sufficient. There you need, let's say, a special electronic or a special part for it, which has then a DC working voltage of at least 1,500 volts.
Okay. Then let's go to the next question. What is the earth leakage current because of Y cap in this 800-volt system?
That's the beauty of DC. There is no leakage current, only in AC systems. So with 50 hertz or 60 hertz, this is an issue. And with DC, it's no issue because there is no leakage current through the capacitors. They are blocking it.
Okay. Then is there any criteria for the design of the listen or just follow the standard?
Yes, let's say the listen should provide a 50 ohm impedance flat from, let's say, ideally 10 kilohertz to 30 megahertz for the most test equipment, depending on the normative you're looking for. So the drawback is the most listens do not have two simultaneously parallel usable outputs, so you can only switch between L or N in the normal listens, so they are not sufficient to measure common mode and differential mode separately. Therefore, we built our own. But there are listens available, for example, from Schwarzbeck or whatever. And the important thing is to provide, let's say, the 50 ohm impedance over a broad frequency range before it degrades.
Okay, and maybe why is it necessary in simulation?
Yeah, we do not simulate the listen overall. We just simulate the impedance in listen, because the simulation shows you the insertion loss, the expected insertion loss from an ideal component with at the room temperature, let's say. But of course, all the parasitics are included in the models from us. And if you include the 100 ohm for differential mode, like I showed you, or the 25 ohm for common mode on the left side, and on the right side on the device under test, then the high impedance for common mode and the low impedance for differential mode, you get a much more realistic insertion loss, like in reality. As if let's say the way in the middle is using always 50 ohm for the listen, that's also fine. Then you get a little bit more deviation to the real measurement.
Okay, and I would say the last question for today, are cutouts under components to increase the effective creepage distance determinant to the filter design?
Yeah, that's common practice to increase the creepage if you make some cutouts. So it's no drawback for the filter in this case. Make sure you have no, let's say, copper polygons under the filter components, not only because of safety, but also because of, let's say, B-field coupling. So only use really micro strips, the classical ones, and no polygons. Then you get the best results. Yeah.
Okay, great. So now we are finished with our webinar for today. If there are any questions left in the chat, we will answer them afterwards via email. Thank you for your attention. I hope you enjoyed this webinar. Thank you to you, Andy. And I hope you will hear us at the next webinar. Have a nice day. Goodbye.
Bye-bye.